Hello, this is Module 5, Naval Architecture for Marine Engineering Extra First Class course prescribed by the Directorate General of Shipping. My name is Krishna Kumar, former ship surveyor with DNV as well as with Indian Register of Shipping. Module 5 deals with two subjects, seakeeping and maneuvering of ships. As with the previous topic of resistance and propulsion, this part, the first part, the seakeeping, also has a lot of theoretical aspects, but I will try to be as practical as possible. There is a lot of internet resources for these topics also, which you could pursue and learn in case there are more, you have interest in certain deeper aspects of the subject. Essentially, the problem or the area of seakeeping and maneuvering are three aspects. One relates to the response of a ship in a seaway. As a ship moves in, there are certain responses when it encounters waves on a seaway. So how does the ship react to it? That is one aspect of it. The other two aspects relates to the course keeping property, how it keeps to the course, and the other one relates to course changing capabilities of the ship. So from a designer's perspective, these are the topics addressed by this field of naval architecture. But before we get into those details, it's important to recap some of the fundamentals of waves, because if you want to talk about responses of a ship in a seaway, you need to understand about waves. I'm sure you could recall your basic physics in school or your engineering subjects. You all know how a wave works. What are the criteria of a wave? The wave height, the wave length, the wave period, the wave direction, and there is a wave frequency. The frequency and the period are important because when it comes to motion, it's important to understand how that there is a wave at a frequency, it is meeting the ship, and ship then has an encounter with a wave. So you will hear these words: encounter frequency, wave frequency, and these are important core subjects. But before we go into, I would just like to demonstrate to you the transverse wave principle. Again, this is. So what you are seeing here is a typical transverse waves. Transverse waves are the ship's waves are transverse waves. And what you are seeing here is a wave going in. Let's assume that this picture, that red dot, is a ship. So the ship does not, though the energy of the wave does move the vessel, the ship does not move forward. The ship just goes up and down to some extent in this kind of a motion. So as a wave passes by a ship, the ship moves up and down. So this is a fundamental principle. That is where the motions of the ship are affected. The energy of the ship transfer, there is an energy part which moves the ship, and the vessel moves up and down with a small cyclical, there is a motion which is set in. This is the essential physical attribute of this whole concept of ship's motion. But in real life, the ship's motions are pretty complex because the waves can be what you are seeing here is a simulation using a software where the ship has a complex motion, and the sea, depending on the wave, the sea encounters the ship, and what you see here is the various degrees of freedom at the motion of a ship. And what you see here is also forces on the ship because of the energy and actions. But this is just for you to get a flavor of what. So when we talk about the ship's motion, it is pretty complex in terms of visualizing it mathematically and calculating it and estimating it. But nevertheless, it is important to have an appreciation of what goes into ship motion and the area of seakeeping. It is borderlining between physics and practical applications of design. So if you look at a simulation, because you have to simulate a sea. A sea is not a regular wave. It's a simplified way of representing it as a wave with a sinusoidal wave. But once you superimpose many waves, maybe you come to, so what you see here is a regular wave, but waves are more irregular. So there is methods by which we are able to predict using theoretical method. Now there are many mathematical methods like computational fluid dynamics. There are theoretical models of Navier-Stokes theoretical exposition. There are energy spectrum approaches. There are quite a few theoretical approaches which I presume is beyond the scope of the current course coverage. But nevertheless, you must appreciate that this is a area of a lot of science and a lot of evolving areas. Now, from the point of view of practical ship design, what will be interesting is how does a ship react to the various seas, because the directions of the sea also varies, and the ship also has a speed, and it has got certain ways in which it heads into the sea. So all these directional aspects of it are important to understand the complexity of being able to design it. But fundamentally on the ship, the captain has got the power to alter the course and the speed. So practically, at the practical level, that is what you got to do. But as a designer, you have to understand how these can be optimized so that life on board the ship is comfortable. Now the ship goes 6 degrees of freedom, as all of you are aware, and it is important to estimate the response in all the degrees of freedom. It is necessary to, this is not only in rolling, it is in surge, in pitch, in sway, in heave and yaw. So all these, you can directly club them into two. One are rotational movements, the other are translations. So when you talk about sway, it is translation. When you talk about surge, it's translation. And when you talk about heave, it is translation. You can say it's a linear thing. The other one are rotational movements. So it's important to understand that these are movements, and it is necessary to, but always there will be a combination of all these movements happening together. But from an analysis point of view, you need to segregate them to view its impact on design and impact on the life on board. Again, when it comes to the sea, representing the sea, the actual sea could be like this, but when you look at a design sea, which would be certain longitudinal transverse sea conditions which are made of, you have to superimpose these things. Now with modern computer simulation, you are able to create these kind of design seas. As you would have seen in many simulations, you can create waves using modern computer imagery. Various types of seas can be created, but these are all created using surface test, using a camera and creating them. And on top of that, there are certain loads to be estimated. There are energy spectrums to be estimated. So it's quite a complex area with mathematics and this thing in this. So that is not within the scope of all. Just this, I put all this just for you to get an appreciation of the vastness of this subject, seakeeping. Now, when a ship moves, what is very important is, as a ship moves with the speed, the waves are coming in certain directions. Ship is also moving in certain directions, and these two have what is known as a frequency of encounter. And this would also have an impact on the way the ship will behave in a seaway. And there the waves, and the ship could be on a wave and a crest. So as we move up and down, as you see, the impact on the motion of the ship takes place. So one has to understand the whole physical phenomena and then use mathematical expressions to estimate them, or using model test evaluate them. So there is one aspect called response amplitude operator, because if you want to compare ships of different motions, how do you compare ships? And so there is it is based from the vibration. So as a ship gets moves around, it is also damp. There is over a period of time that motion is getting reduced. They are reduced basically, it is like the spring in a typical vibration, which you are all very familiar in the mechanical area, the damping effect of vibration. Similar to that, in a ship there is the viscous forces which dampen the motions. And also there is an added mass effect, that is the water moving along with this thing, which again reduces the motions. So there is a natural damping effect on a ship and a seaway, and then there are also periods of oscillations, and there are certain factors called tuning factors. So all these things can be simulated with a theoretical understanding. One can arrive at the periods of the motion and then relate it to the amplitude of that particular oscillation, and then come out with a concept called response amplitude operator. So this is one way. For instance, here it gives a surge ROA of 0.5, which means the wave height of 4. Can give you can compare that to between ships, for instance. What is the meaning of it? So the excitation, that's the waves in the wind, and the ship's ROA leads to some response. So this is how the calculations can be presented in a seakeeping study. So responses are the output, and the inputs are the excitation, which causes the vessel to turn around, which is the wind and the waves. So these are the models on which seakeeping data is presented. Now another aspect along with this, for instance, this is a picture of a wave coming and hitting. The wave carries some energy with it, and there are also methods of estimating the frequency of the waves to the energy of the waves and the direction of the waves. Now there is the energy spectrum, which is also another design approach towards calculating the response amplitude. Essentially, this approach also leads to essentially looking at the input waves in terms of spectral density, and then looking at the output of the ship's motion. So you could study how the effect is and compare ship design. So these are all seakeeping studies which are done. Model testing, you could simulate. These are large seakeeping basins available in certain institutes. Even India has got excellent seakeeping basins where you can simulate waves and put the models and study the operation. So you can create a model and study the type of responses you can get. So there are seakeeping bases. In IIT Madras has got an excellent seakeeping basin. Pune Central Water Research Station. I think IIT Kharagpur has also got it. So these are areas where one can do seakeeping studies. Now, why this is important is, with this picture is very evident that these have relate to safety of the ship, to the living on board the ship. So there are issues like the wetness of the ship, how throw water over the forecastle if you are slamming too much. So these motion studies help in designing the forecastle, shipping water on the side. There is a 4-foot emergence in severe, can lead to structural loads. There are practical implications, and it's necessary to study these loads. But of course, as I said earlier, the simple solution in any kind of a seaways is to keep the course and speed, alter the course and the speed, which the master does that when they see the types of sea. Now, there are also other data available in terms of correlation of the waves in certain wind and waves, such as a Beaufort scale, and there are significant wave heights. These border now into oceanography and finally the study into ship design and into so if you look at this overall picture here of all the types of waves, there are ordinary swells, the tide waves which are on the shore. Then you have these long period waves. Tsunami is a long period wave. While a tsunami does not have too much of an impact in terms of energy spectrum, you can see here it is much less than the wind waves because in the sea, the tsunami wreaks havoc near the shore, because that is where the energy builds up. While if you see the wind waves, this is the energy spectrum of the waves, and what you see here is the normal wind waves which we encounter, where the frequency is between 0.5 to 30 seconds. waves in the sea. So these are all correlated as a science which is evolved, and this is how the seakeeping studies are done and interpreted. Now coming to the area of maneuvering, as opposed to seakeeping is to study of the motions of the ship, maneuvering relates to the directional stability. The ship must keep course straight, and at the same time it should turn. So it is the turning is done with the rudder, as you can see here, and for example a starboard rudder here will give a force here and it turns, and there are certain motions associated with when the ship turns. There is also a heeling effect. It has an effect on the stability. So these are interconnected. I will come to that a little later. But what creates a course keeping ability and what gives a course changing ability may have a relationship on the design aspect. For instance, in the after part of the vessel, there is the skeg or after body that gives the ability for the vessel to keep course, while the rudder gives the ability for the vessel to turn course. So if you look at the aspects of the turning, so the turning ability which is given here, a good turning ability is able to turn in with a short turning circle. So controllability and turning, these are all interconnected, and these are all very much related to the afterbody design and the ship rudder design. So there are two important tests in this. One is called the turning circle test, and the other one is the zigzag maneuver. There are also spiral maneuver test. So these tests are also done to ascertain what is the final design performance of the ship, and these data is available on board. One important point which I would like to add here is a concept of a pivot point. Where does the ship turn around? So there is an imaginary point on which the ship turns around. Now, the rudder force acts as an imaginary point around with a center line of the ship, which is a pivot point on which you give a thrust and the vessel turns around it. So for instance, this could give a good theoretical example of how a rudder effect happens. A rudder has the starboard rudder is given, and the force, again is an aerofoil shape like the propeller. You get a thrust force, and that causes a rudder movement here, which makes a vessel to go to starboard. So the rudder force to you can say the pivot point or the CG, and creates a hydrodynamic movement, and this is what causes the ship to turn. And the rudder is an aerofoil shape here, and it is almost similar to what I explained in the propeller, how the thrust forces are developed. And there are many types of rudder design, balanced rudder, because these are all related to saving of the power related to turn the rudder, the various designs of a rudder. Now there are a few more topics as per your thing is to do with the turning circle, the zigzag and maneuvering trials. I mentioned a little bit on the topic. So the maneuvering trials, here a ship is on course, and then the rudder is turned around, and in various the rudders are applied, and the ship comes into a steady turning circle. And then you measure these, you have plotted and measured these things. So these are all data will be available on board, and during this action the vessel will also heel around. There is a ship will heel around a turning because of the effect of the centrifugal and the centripetal forces, and these are also plotted in a practical thing in the maneuvering trials on a turning circle test. There is also similarly a zigzag test. The zigzag test is to some extent reflects the course changing ability, and again the rudder is given to both directions, and you check the change of the heading. So the rudder angle is changed to both sides, directions, port and starboard, and then you look at the ship's heading, how they change, and this is also plotted and available in the zigzag test available on board. So from a perspective of standards and data on maneuvering and seakeeping, or rather more on maneuvering, you will find the turning ability. This is now taken from an ABS standard, an overview of standards, which talks about the measurement of maneuverability, turning ability, which is the tactical diameter in a turning circle. They have given certain standards. There's an IMO standard, and there is also some ABS. Every class society has got these requirements. The turning ability, the course changing or the yaw checking ability. There are overshoot angle relates to the zigzag maneuver. Then there is the initial turning ability. The stopping ability is also important to crash stop. It's part of the seakeeping trials. So what is the crash stop test? What is the level you can get the vessel to stop? And similarly, the straight line ability or the course keeping ability. There's a pull out test, residual, but these are all not optional tests. Width of instability. If you are in a warship design, these are all very important, because these kind of maneuvering and interceptor boats, etc., these becomes very important. So with that, I come to the end of this topic. Which is a deep subject in naval architecture and theoretical basis. So we have covered almost all the topics